Well, I used to work at GitHub, and as many people have seen of GitHub, we've had quite a couple outages. And when those outages occur, there are some issues with refunds, inconsistencies in data on the dashboard, and the way we calculate our revenue. And today I'll be talking about the difference between our Cosmos database and also the Redis cache we use to basically update people's cost centers and show them the costs they used. So my name is Michael Levin. I did used to work at GitHub, but now I am building a Y Combinator startup to build the company brain for all your financial operations. What cache drift looks like at 3 a.m. So I actually used to be an intern at GitHub, but we weren't staffed that much, especially with the new wave of AI PRs, and there were a lot of people who had to help out with the billing system. And I was one of the only backend engineers on my team, so I was tasked with actually porting our old monolith billing system to a microservice to make it able to be faster and to be able to handle the new amount of PRs and new amount of actions usage. Phantom charges. We had a lot of billing charges that were actually billed twice. So what would happen is when a payment would retry, we would actually never give it a key. So what would happen is it would retry twice, and we'd actually be billed twice. This happened many times over. And what would happen is it would eventually lead to a state that was inconsistent about almost 5% with almost all our clients. And we'd go out and we'd refund each one individually. Another issue was stale bounces. So what would happen is when we sent basically a transaction to Redis, it wouldn't always be written actually in Redis. And when it's retried, it actually would never be written to Redis. But we use Redis for our UI to basically put in the values for that. So people would actually see a different bounce in their cost center than they had, or a different amount of credits than they had. So for example, someone would want to use GitHub Actions. It would say they had actions left, but the actions would actually be at 100% in our Postgres database and never be updated. Then we had a lot of reconciliation. That was really tough. So what would happen is we wouldn't actually know where our source of truth was. So we'd have a source of truth with Redis, and we'd also have our basically Cosmos DB, basically source of truth. And what would happen there is we'd build dashboards for our financial team with the Redis dashboard in place. And what happened was when they actually checked our charges, they actually didn't even exist, or the ARR would be completely wrong. So this is called cache drift. It's when the source of truth of Redis actually diverges with the Cosmos DB. And this is what led to a lot of problems with GitHub, and is why our billing team, I used to work there, so our billing team was 15% of all our engineers at the organization. Money has memory latency and lawyers. So basically money, you always have to have a record of it. You can't just have it in a Redis cache. It can't just be stored for, let's say, a couple days. It has to be stored for 3 years. So we always had to have it in our Cosmos DB. But what would happen is when we had so many requests coming from all these AI PRs and all these new billable metrics, we couldn't just use our Cosmos DB. We had to use Redis in front of it to cache it and update our front end. And every write, though, had to be auditable. So we always had to put it in our database later. But what was happening with AI and people doing PRs is they would not always use our database as a source of truth. And retries were incredibly dangerous. What would happen with retries is we try to send a retry to our Redis, but then it would fail. And then it might also fail on the Postgres side, and then we'd completely lose transactions. Another thing that happened was the cache was on the critical path. So when people sent over a transaction to Redis, it would need to go to Redis because we needed the reads over there because we had so many different transactions coming in with millions of new billable metrics a day as our PRs had increased over 1,000% with everyone vibe coding and doing AI PRs. So we really needed to have an accurate cache so people could see it on the UI. Here's the anatomy of drift, which I assume many of you guys have seen before. Example of failing on the cache, but being in the database. Another example is it goes to the cache, but then it fails to the database, where it's going to retry and basically fail open. And then there's an example of where both updates fail, and that's when GitHub went down, and you guys saw all those messages. We have to always basically trade consistency with latency. But in billing, that's very difficult, because when you see your credits have hit 100%, but you're actually still able to use credits, or when you see that you have credits available, but then your requests are failing, that's when it leads to a ton of support tickets. So the drift comes from that when things are written to both Redis and the database, they're written differently. They're in separate, basically, actions. So what would happen is we send one action to Redis. It could retry on Redis and then fail, but then it could actually work in the database. And that leads to an inconsistency. There are three root causes to this. So a partial failure is, as I talked about before, it would succeed on the DB, but then it would not succeed if the cache, or the cache would have a stale value, and you have to invalidate the whole cache, which would lead to a long time of it updating and lead to wrong values in the UI. Then there will also be retry loops, where it would continuously retry to the database and also the cache. This is a huge problem, as we'd fail open, and then we wouldn't actually have an updated value for our ARR, and sometimes these would be lost if we basically had too many at a time, and then we could not deal with the retry storm after of how many transactions were coming. Another thing we had was a problem of async replication, where when we were trying to replicate from our database to our cache and send it over, it would actually fail, and then we would have a wrong UI for a really long time, leading to multiple support tickets, as the UI was controlled by our cache. 4 patterns that stopped the drift. One pattern was providing a unique key. This means that every retry would never be double counted, and it would only be counted once. Another one is a continuous background sweep to provide replication, so we could basically make sure our cache was in line with our database and invalidate the cache if it wasn't, to make sure our UI was correct. Another one was making sure DB and cache updates were inside one transaction. So when the cache was invalidated, it would happen at the same time as there was detected of drift. Another thing was the page and divergence, not just errors. When drift was a real signal, and we actually had a major amount of drifts, as drift would be very frequent.